The broadcast is now starting. All attendees are in listen-only mode.
Hi there, René Fabrizio speaking. Good morning, good afternoon, depending from where you're joining this session, and glad you can make it today. Today I'm here with my colleague Vladimir Marchenko presenting how to deploy secure IoT devices by making use of MDK. Vladimir is probably known to the majority of you as a product manager for MDK Core. He will run the show today and support at the end of the session the question and answers. As usually, please, at the end of the session, please place your questions via the chat window in the portal. And also, as used to do, you are on mute by default of the system. I will stop now with the introduction and let Vladimir take over to start today's training session. Vladimir, your show, please take over and kick off.
Good morning, everyone. Good afternoon. Welcome to this webinar today. In this session, I will talk to you about deploying secure IoT devices using ARM processors, ARM software components, and tools. And the agenda for the session is following. First, a brief rationale: why do we need this, and what do we need for secure IoT? And then I will show you how we are securing IoT devices at ARM. Next, I will go through the SAMSys components, software components that help to deploy IoT devices at scale, including a microvision project and a demo connecting an IoT device through the Wi-Fi to AWS cloud. And we'll conclude with a summary followed by your questions. So IoT devices are different. So we know they now already available in all different environments at our home, buildings, on the streets, industrial environments, and so on. They all hold different different characteristics, and it makes it sort of difficult to have a common ground for them. But it's still very important to ensure that the IoT devices really become mass adopted and used by everyone. So there are different aspects and different challenges here, from connectivity to device themselves, ease of use, and so on. But the aspect I want to cover in the session today is the security, and you have heard about it from us many times, and it stays extremely important. It is crucial to ensure that the devices, IoT devices, are secure, that the devices can be trusted, that the data that they can collect can be trusted, to ensure that the decisions made based on that data are really meaningful and correct. So first, let's look at how we actually can bring the security into the device, how ARM helps to do this. We identified this problem early on at ARM, and it was clear that this really needs to go into the hardware level, into the architecture. And that's why the so-called trust zone technology has been added on the Cortex-M device family. So here you can see it. All our latest processors on the Cortex-M have the trust zone technology as well. The Cortex-M 33 and 35, and also the latest addition with the optimization for machine learning operations. It also has a trust zone, because this is really crucial to ensure security on the device. This is our ARM v8M architecture that has this trust zone technology. It has been available on the Cortex-A devices before, so on the devices that go into the smartphones, where the security problem was identified early on, and it became clear that also the smaller devices that are used for sensors, actuators, also need this sort of security on them. So what exactly is this trust zone technology, and what is the idea behind that? The idea is pretty straightforward, is to separate the device into so-called trusted area that is secure and isolated, and everything what happens there can be trusted, and then non-trusted is basically everything else. And that splits the device in two parts, starting from also on the hardware, the microcontroller resources. So the CPU registers are split into secure and non-secure. Okay, can be split. It's an optional division. It doesn't need to be done mandatory, but if we want the security on the device, then we need to split it. The device memory can be allocated to be secure or non-secure, all the peripherals as well. Right. So this is the trust zone technology that enables hardware isolation on the device. On top of that, the projects or the firmware and the user projects are also split into the secure and non-secure. And the secure part performs the system start, ensures that the system is intact and can be started, and it also keeps all the critical security functionality required for key storage, firmware update, and so on. The secure part can access also non-secure resources, but not vice versa. So the user project is considered to be non-secure. It can be attacked, and it cannot access the secure resources except only through the predefined APIs that needs to be implemented properly to ensure that there is no leakage of the secure data possible. Right. So this is basically the idea behind, and a simple view at the trust zone technology implemented on our ARM v8M architecture. So the architecture is already on the market for probably 3-4 years, and there are multiple silicon partners that already have brought devices with the Cortex-M 33 and 23 cores on the market. There is a kind of a second wave with additional optimizations coming, so it gets really traction from our partners, and also our ecosystem partners adopted this architecture with the compiler, toolchain, debuggers, operating system, software components, and others being ported and became available for these latest devices from the chip vendors as well. So this the trust zone and ARM v8M basically solve the problem on the hardware level. They bring the hardware isolation where security can be kept in the separate area, not easily accessible to an attacker, or when properly done, not available to an attacker. But that's actually not enough for an IoT device. The security is an extremely complex topic, and there are multiple functionalities required during the life cycle of an IoT device, starting from the device identification, authentication, connection to the cloud, right? So the firmware updates, and there are multiple steps that end users want to do with this device. And having the hardware isolation is great, but it's not enough, because the software needs to be present as well. And implementing the software correctly is a great challenge as well. So that's why we at ARM went a step further and came up with the platform security architecture, PSA, that you probably heard about as well, that basically looks at the IoT devices, analyzes the common threats, right, and through the whole life cycle, and defines the firmware architecture and hardware requirements that allow the device to be actually secure. And on top of that, we bring a reference, or we bring a reference implementations in the open source that can then be used by the vendors or OEMs. So there are multiple use cases have been analyzed, and the common principles were found that are required in multiple use cases. This is the device identity, trusted boot sequence, software secure over-the-air software update, and the certificate-based authentication. And that was is on the high level. It is split more into individual functionalities, and from there, these particular architectures and requirements are defined by the PSA. An important concept of PSA is so-called PSA root of trust, that is a kind of joint hardware and software system that separates critical security functions from the rest of the system. And it can be then used for crypto, so encryption and decryption, attestation, secure storage, and trusted boot. And it needs to be implemented by the chip vendors, or supported by the chip vendors, to ensure that their device can be actually trusted. To access all these functionalities, PSA also defines so-called PSA functional APIs that then the non-secure project, non-secure software can use to access all these secure functionalities. And that actually makes the device secure from the PSA point of view. And using a device with the PSA root of trust and the exposed APIs really enables the secure connection of the device to the cloud. So that what PSA has defined on the software and architecture level, and a reference implementation for that is called Trusted Firmware for Cortex-M, or TFM, an acronym you heard many times as well. So this is just a reference implementation of PSA requirements, and as shown here, it implements really this functionalities defined by PSA, attestation, cryptography, trusted storage, with the APIs defined by the PSA that can be accessed from the non-secure areas, right? So using this PSA functional APIs. There is also a possibility for users to add their own services, security services, and the TFM is implemented on a real hardware, or on the real hardware platform, and the TFM is hardware hardware specific. So the reason for that It's so hardware specific. I mean, is the device specific, vendor specific for a particular device. The reason for that is because we of course use a lot of architecture resources that are available on any ARMv8M, but many features or many functionalities require use of device-specific peripherals. For example, for flash writing into the flash in this internal storage, internal cluster storage, it writes to the flash, and is done differently on every device. The different crypto engines can be available, and this is again is device specific. So that's why it, the APIs are same, but the implementations are then unique for every device, and they use the HAL of specific device. So with that, we basically have the security at the hardware level in our architecture. We have security, all the analysis of threats and life cycle of the device with the requirements and APIs defined and functionalities for the security blocks, and we have a reference implementation with the trusted firmware. So with that, we have a basis and a concept in the required to make the device secure. But that again is not the end of the story. The device now needs to be connected to the cloud, right? So we make sure that the device can keep secret information secret, but it also needs to be now connected to the cloud, and that's where the census and that's not just in a specific way. It's with all potential flexibilities that the embedded world brings or enables to the Cortex-M devices. And our vision is to really make low power IoT, and not just IoT, but also AIoT, so AI on the things, to be easy on Cortex-M devices, and to bring a platform for building and deploying IoT devices at scale that are accessible to any developer on any device with any operating system or IoT stack, and that can be connected to any cloud, because this is really brings it and enables this scale, and it all works seamlessly together with the ARM ecosystem. For that, we have a strong basis with more than 250,000 users, more than 7,000 microcontrollers already supported out of the box, with multiple operating system and IoT stacks supported as well, and different IoT connectivities enabled on the devices too. So the approach for an IoT on Cortex-M is shown in a simpler way on this slide. So the security part is really where the trusted firmware and the PSA concept get into, and here all the functionalities common for the IoT devices are implemented: cryptography, storage, attestation, secure boot, and whatever else can be required here. And we have the concept and divisions on the device or board level with the census. We have an RTOS for threat and resource management, and again with the census RTOS, this also works not just with one specific RTOS, but with several, also enabling simple switch and selection of RTOS of the interest. The secure network interface actually brings the connectivity into the system, right? Because the device needs to be connected, and this also needs to be flexible and secure. So this is achieved with the secure network interface that I will explain a bit more in the next slide. Cloud connector allows brings the protocols required to connect to the specific cloud, and the device logic is finally implemented on the user application. So, and all that is componentized and configurable and available for users to choose from, with just the main logic required to be implemented in the user application. So if we look closer into the secure network interface, here with the CEMSIS components and MDK middleware, there are multiple choices available for the users, and that all lead to the same result. The device gets connected to the cloud, and as you can see, the upper layers that are used are same. That really enable the final connection to the cloud, and we support also multiple all common cloud services: Azure, Google, AWS, ARM, Pelion, and IBM Watson. And the differences then come really depending on the device. If it's an Ethernet-based device, then a middleware stack from MDK can be used, enabling the TCP/IP on top of the Ethernet devices. Some third-party options are possible as well with LVIP implementation. If this is a Wi-Fi device, we have a CEMSIS driver that also enables the IoT socket connectivity through the CEMSIS Wi-Fi driver API, and then through the Wi-Fi signal to the brings it connection to the cloud. The security is implemented also in the same way using Mbit crypto. And again, if there is, so this is the common view that works also on the devices without trust zone. So all the common Cortex-M 4, M7, M3, M0 devices can be run in the same with the same components. The difference that ARMv8M brings is really this concept of trust zone, and the TFM isolated in the secure space for managing of the secure information. But the connectivity side and the components are exactly the same as for the ARM v7 or other architectures. Okay, so the next, let me go and show you the real example that is based on this concept. I will. So this is slide. It summarizes probably what I will show in the demo. I'm using a Nucleo L55. This is a Cortex-M 33 device from ST. That they have just recently, or probably a few months back, they have launched it publicly, and I will use a WIZnet Wi-Fi shield that just gets on top of this Nucleo board. It's an Arduino shield that easily connects to the Nucleo board. I'm using a ST-Link debug connector for the demo, but also the ULink Plus or ULink Pro can be used. There is a corresponding port on the board that, and we have an adapter for that is included with ULink Plus and ULink Pro that can be connected to this ST port, and then the features of ULink Plus and ULink Pro become available as well. So let me just switch to the project. It is currently available in Census. Sorry, it's currently available in the GitHub, but we will finalize it there a bit more and publish as a reference spec example as well. So, but before this is done, I'm just using the example directly from the GitHub. So here it's a multi-project workspace, right? So that has 3 projects, and one project is really the TFM implementation for this Nucleo L55 device. It doesn't use anything from the board, so it just really targets the L55 device, and it doesn't need to be specially configured, except maybe let me show you what's inside. There are some specific components that we use from the security, from the TFM. We use the TFM core, and we use so there are multiple components, as you can see, and functionalities. So we just use a crypto service just for encrypting and decrypting data, and we use internal trusted storage for storing the certificates, or for storing the private key, actually, in the end of the device. The private key is kept securely through this interface. There are other items for logging, attestation, secure storage on the external device, etc. Some testing services, but it's we don't use it. You can all read more about this in the TFM documentation, but in this example there is nothing more to do here. So what it does, it implements the TFM on STM L55, and it is already configured to be put into the secure area. There are some definitions in the linker script. How it is split. So this probably maybe if you need to change something, this is the area where you can play with assigning more data, more resources into the TFM part, etc. But from the box we can just build it. It might take some while to build, so it's already pre-built on my side, and gets done pretty fast. So what I just need to do is load this on the device. Okay, and that's pretty much it. So now we have what we have is this trusted firmware part present in the secure area of the device, and the device is configured correctly for the secure and non-secure parts, and the trusted firmware is loaded here as well. Right, so this is this TFM secure firmware project. It's present now in the device. Now there is another project. The second project, AWS MOTT provisioning, is sort of is a temporary project, and it's just a demo how you can bring as a key on the device, because here we don't have any device identity. We don't have any device security keys yet. This needs to be provisioned on the device in some way. And this, depending on the device design, this can be done manually. This can be generated by the secure firmware itself. It can be, well, it can be provisioned also over the air. There are multiple ways that are used for that, but in our case, we wanted to make just it very simple and provide a temporary project, or temporary that it runs just for a short time on the device and stores the key, puts the key into the secure area of the device. So the key itself is needs to be configured in this header file. So it has a called IoT Demo private key. It's pretty long key, and where does it come from? Let me show it to you. It actually, it's in our case, it is generated by AWS, but it can be also generated by the user and uploaded to AWS. So there are also different ways to get it. Critical, it needs to be in the right format. And let me show you how it works in the AWS. In AWS, we have, so this is the starting page. They provide multiple services, and one large area, important area, is Internet of Things connectivity with IoT core. If we get into IoT core, we get the view on the on the recent connectivities and some sort of a dashboard that can be configured. But what is important is this so-called things, and these are the devices in AWS concept. And here we can create and add new things. And this is my thing that I will use during the demo, called Demo Device 1. We can look into it, and to every thing or every device, you can connect a secure certificate, or even I think multiple certificates. And when you create this certificate, it actually also gives you the private key. It provides the private key, public key, and the certificate that can be used with the device. I'm sure I can obtain the private key after that from here. So this, I'm not fully sure how you can do this, but once the certificate is created, you have the private key for the certificate available. It can be connected with the device, and after that, this private key needs to be provisioned in the TFM. And this, so here we do it just in a plain text, so absolutely non-secure. It is available as a project. This is again just an example how this can be done. It's more for understanding where things come from, because of course, if everything is super encrypted, super secure, it becomes just too complex to follow. So we can build it. And here the best way is actually to start it with the debug, because then we can see the result of the provisioning. So now if we run the device, it says AWS IoT key provisioning done. And that means that all worked well. We were able to use PSA API and provide TFM with this key, and was accepted. It's stored. So it's there. If something goes wrong, if the format is wrong, then it just prints failed, and you need to investigate what is the problem. In most cases, it's just the key format is not correct. Okay, so we have the key present in the secure storage as well. And the next step is really the user application that is runs in a non-secure user project. And you can see we use lots of packs here to implement this project, and lots of components. Here is just some references. What component comes from what pack, and how does it map into this view of this on the split of our cloud connectivity. So we have some device drivers for the Wi-Fi. We have IoT socket implemented in the client and utility components. We have the security with MBTLS, and what we also have is this TFM block. And the TFM component is needed here just to ensure that the API is available for the project as well. So we don't use anything else. Of course, we don't use any of this functionalities because they are running in the secure area, but it's just uses the API to access the TFM functionalities. So we can switch back to here, and here's again the same view. What needs to be configured here is basically, because this is a Wi-Fi-based connectivity, we need to provide the Wi-Fi credentials. We have a separate defines for SSID, password, security that gets passed to the Themsys driver, and then Themsys driver again correctly provides it to the Wi-Fi device, the WIZnet in this case. But you can also see that we have multiple targets as well, depending on your Arduino shield, on your Wi-Fi shield. We support SparkFun, WIZnet, Inventec, and so others might come in the future as well, or it's then makes it clear how you can really support it with a different Wi-Fi shield. So the Wi-Fi connectivity is configured here, and another option, what we also need to configure is the connectivity to the security and connectivity actually to the AWS server. We need to provide the address, so where actually all the data needs to go to, and this comes from, let's see if I can easily find it. So this comes from this test gateway. So we have a dedicated IoT console that or endpoint that is that AWS kind of provides for us, and this is just comes the address just comes from here. The next AWS parameter is so the port is I think it's constant all the time. Another credential is the Amazon root certificate that is we need to provide here. It actually always the same because it's same for it's made by Amazon. It's same for all devices and all for everyone, and you can find it in the documentation of the AWS. So there is a lot of documentation, very useful. You can learn a lot from there. But for the security, there is this server authentication, and that's where we need to authenticate that we are connecting to the correct server. It explained what it is. And then there is a list of certificates, and one of them is Amazon root CA1. That's exactly that we need. So you can just we can copy it from here and provide it as a IoT demo root certificate. The next parameter is demo client certificate. That's what I have shown to you in the configuration when we created a device, and then the device had a certificate. This is basically it, right? And this is a certificate that corresponds to the same private key that is stored, that has been provisioned in the previous step and is now kept in the security area. The rest we don't need to configure. It stays empty, and with that, so with private key we don't need to provide here, as it comes from the TFM, will be obtained from the TFM. If we run this on the device that doesn't have TFM, then we can just provide the private key here. It is much less secure, but the demo will still work. The IoT demo identifier, this is the name of our device. It again corresponds to the device defined by the things here. Okay, so this, I think, pretty much what needs to be configured. There are some, this is the what I mentioned, the TFM API that we are using. So that again also can be checked in the corresponding TFM API. We just selected it. We don't use anything from the TFM components themselves. Okay, so now the device is pretty much ready. So we can compile it out of the box. It compiles. I think because it was pre-compiled on my side to save some time, there are some warnings explaining that the configurations. Some configurations are not set to be used in the production, and that's of course on purpose. We are doing here a development project first, and once we need to move to production, then some settings needs to be changed. And we install the debug on the device, and the firmware gets loaded. And the way we do here the login, so you can before we start it, right? So we just print some messages in the debug with the printf that are redirected using our event recorder, and what we need to do in the AWS, we need to go and actually subscribe to these messages, and the MQTT protocol is used, so we need to subscribe to MQTT messages, and AWS provides this sort of MQTT client. I think you can of course try to do something differently, but this is our default approach. And if we use the just the hash symbol, it means subscribe to all topics, whatever they come. We can maybe specify not to auto format it into JSON, but just to use payload as a string, because this is what we are sending, some strings. And when we subscribe, then the topic appears here, because you can then finally, you can have multiple topics, multiple kind of signals you're interested in. We just take everything, and when the data starts coming in, it will be shown here, right? If all this is correct. So we can go ahead and run the project. First, it connects to Wi-Fi. Using our component viewer, we can see how it's what components are doing. Now the connection is done. We publish 9 messages, one after the other. We wait some confirmations, and then the demo is completed. We do some analysis how it went, and it says demo completed successfully. If everything was correct. If we return back to the AWS, we can see, yes, there were, we published, it has received published messages, it has received the hello world, so the hello world messages, one after the other, so the connectivity worked correctly. And so, and that's a reference example that we will use on for lots of things, for different aspects, but that's basically the starting point for us to ensure that connectivity to the cloud works, and it's easy to move across different connectivity options, clouds, and etc. So what this is just again the view, how it went, the connectivity, the view from the debug console, and the view from the AWS console. So here it shows some green messages, or highlights it in green, because the JSON formatting was used, and there was some, yeah, it wasn't in JSON format, so it just complained about that. So what we're going to do for users, so we are updating, or we have the web page KEIL.com IoT, where we list the current ports that we support and platforms that we support. Most of them will be ARMv8M, but also with Trust Zone and with TFM implementations. But some are not, don't have a Trust Zone, like this one, MIMX or F7 L4 devices. They don't have it, but still the demo can run just without utilizing the Trust Zone and TFM. And here you would find this example properly, or the package with the examples, additional descriptions, and documentation as well. So coming to the summary, ARM takes a holistic view, so the whole view at the development cycle and life cycle of IoT endpoints, providing the security from the architecture, hardware, all the way through the software component and tools, right? So we need to also ensure that our tools, like compiler, can properly handle this security split. Our Temp Zone tool enables users to assign the microcontroller resources, memory, peripherals, and etc. To the specific secure or non-secure project. And we have a software architecture, or more platform architecture with hardware and software aspects covered. Our PSA that ensure ground-up security in devices, and the TFM is a reference implementation that we use, and it's open source, that the chip vendors will be using on their devices as well. Finally, our entry page for IoT, where this information and many upcoming aspects on bringing IoT and scale securely will be covered. Okay, so that was my part. Thank you very much for your time. If any questions, please provide them to me, or if any questions later, feel free to contact me directly as well.